Hello class, welcome to the Stat 215 Lecture 24 video. In this video, we're going to focus on two objectives. First, we want to conduct a hypothesis test for the population proportion P. And second, we want to conduct a hypothesis test for the difference in two population proportions, P1 minus P2. Let's begin by looking at our first objective. If you recall, a hypothesis test is a standard procedure for testing a claim about a population parameter. We will follow four consistent steps. Step 1, state the hypothesis. Step 2, specify the model and check the assumptions. Step 3, calculate a test statistic and p-value. Step 4, state your conclusion in the context of the problem. Let's begin by looking at a hypothesis test for one population proportion. An example of this is the proportion of defective items in a manufacturing process is less than a specified value. A second example is the proportion of voters who prefer candidate A greater than a specified value. As we are working with population proportion, you can imagine that the parameter of interest is going to be P, where P is the probability of success in a binomial experiment. We'll be focusing on our hypothesis test. Our null hypothesis will be P equal to P naught versus the one of three alternatives. P not equal to P naught, P greater than P naught, or P less than P naught. And we will have our evidence based on a sample size n and number of successes x. A lot of what we did in our previous two lectures are going to have applications here, only it's adjusted for proportions. Let's begin the hypothesis test for P when we are dealing with a small sample. This is going to be a little bit different than what you're used to. The test statistic is going to be the binomial random variable x with p equal to p naught. To calculate the p-value, we have four separate situations. When our alternative hypothesis is p greater than p naught, our p-value is going to be the probability of x less than or equal to x. When p is less than p naught, our p-value is going to be the probability of x less than or equal to x. Now, the even more unusual case is when we're dealing with our two-sided hypothesis test. Our p-value is going to be 2 times p, not 2 times p, 2 times the probability of x less than or equal to x when x is less than n times p naught. However, when x is greater than n times p naught, then our p-value will be 2 times the probability of x greater than or equal to x. Let's go ahead and take a look at an example of this because I know it can be a bit confusing. A builder claims that heat pumps are installed in 70% of all homes being constructed in Richmond, Virginia. A random survey of new homes in this city showed that 8 out of 15 had heat pumps installed. That's about 53%. Does this provide evidence to conclude that the rate for all homes is different from 70%? Okay, let us say that alpha equals 0.05. A couple things that we should highlight in this problem. One is that we see the word difference. At this point, we recognize that that means our alternative hypothesis is going to be not equal to, and this 70% is going to be our p naught. Of course, our alpha level of significance is going to be important. As we stated before, our test statistic is going to be our binomial random variable x with p equal to p naught. Our random variable x in this case is going to be 8 because we are talking about that 8 out of 15 had heat pumps. Using this information we've highlighted, let's go ahead and take a look at how to solve this problem. So first off, we have our first step, stating our hypothesis. Our null hypothesis would be p equal to 0.7. Our alternative hypothesis will be p not equal to 0.7. Our test statistic will be our binomial random variable x with p equal to 0.7 and n equal to 15. I apologize if we struggle or if we scroll back up, I forgot to highlight 15 as our n, and as I stated, 8 was going to be our x. Scrolling back, again, x is equal to 8, and in our case, n times p naught is going to be 15 times 0.7. This is going to equal 10.5. If you recall, again, scrolling back up 2 slides, since we are working in the case where our alternative hypothesis is not equal to, we are going to have to base our calculation on p-value, whether or not x is less than or greater than n times p naught. In our case, x was 8, and n times p naught was 10.5. This is clearly a case where 8 is less than n times p naught. So that means to calculate our p-value, we are going to have to do 2 times the probability of x less than or equal to x. To plug in, this means our p-value is going to be 2 times the probability of x less than or equal to 8. Using our skills on how to find probability in a binomial situation, we know this would be equivalent to 2 times the summation of x equals 0 to 8 for the binomial distribution where n is our sample size and p is our probability of success, which is 0.7. We can use the binomial table to get that probability. We could also calculate it by hand. So this would turn to be 2 times 0.1311, which would give us a p-value of 0.2622. Now we can go ahead and make our comparison. We can see that 0.2622 is greater than our alpha value of 0.05. This means our decision will be that we do not reject the null hypothesis. And our conclusion will be that we do not have sufficient evidence to say the heat pump installation rate differs from 70%. Very good. You may want to consider redoing this problem at home because I know it's different than what you're used to. Let's take a look at another situation, in this case when we have a large sample. This is going to seem more familiar to you. In this case, we have to address the following assumption, that we have a random sample from a large population such that n times p naught is greater than or equal to 5, and n times 1 minus p naught is greater than or equal to 5. We assume that our statistic p hat follows the normal distribution with mean p naught and standard deviation square root of p naught times 1 minus p naught over n. Our test statistic, also known as a one proportion z-test, will be z equal to p hat minus p naught, all divided by the square root of p naught times 1 minus p naught over n. Notice with the test statistic we said z equals. That should be an indicator to you that we are going to be using the standard normal distribution. So in order to find our p-value, we'll be using the standard normal distribution. Let's take a look at example 2. The DMV in a large city claims that the pass rate for the driving test is 80%. In a random variable of 90 local test takers, 61 passed the test. Do we have evidence that the pass rate in the city is less than 80%? Let alpha equal 0.05. For us, our parameter is going to be p equal to the proportion of all candidates who pass the test. Our null hypothesis will be p equal to 0.8, and our alternative will be p less than 0.8. We can see this by the last line second to last line in our example problem, where we asked if the pass rate in the city is less than 80%. Our p hat will come from our sample of 61 out of 90. To check our assumptions, we have n equal to 90 drivers, which means we have a large random sample from a large population. P hat is going to be 0.80, as we determined before, P naught is going to be 0.80, and P hat is going to equal 61 over 90. If we simplify this, it's going to be 0.678. To check the rest of our assumption, with n p naught and n times 1 minus p naught being greater than or equal to 5, we can see that 90 times 0.80 is going to equal 72, and 90 times 0.2 is going to equal 18. Both of these values are greater than or equal to 5, so this means our assumptions have been met, and it's okay to use the normal model to perform our one proportion z-test. So at this point, we know our sample size, our p naught, and our p hat, and are very easily able to calculate our standard deviation, so we can go ahead and calculate our test statistic z. By plugging in the appropriate information, we will get a z statistic of -2.90. Using this, we can calculate our p-value. If we use StatCrunch, we can go to Stat, Calculators Normal, select our mean to be 0, our standard deviation of 1. Since we are trying to find the probability of z being less than or equal to -2.90, remember our alternative is less than, in StatCrunch, we'll also click less than, and then we will enter our appropriate test statistic of -2.90, and then select enter or compute, and we will get a p-value of 0.0018658. That's pretty small. So this means that the probability of taking a sample of 90 test takers and finding that 61 or less pass the exam when the true pass rate is 80% is 0.0019. Since 0.0019 is less than our alpha value of 0.05, we can firmly reject the null hypothesis. This will leave us to have a conclusion that at the 5% level of significance, we do have sufficient evidence to say that the pass rate is less than 80% in the population. Let's go ahead and look at a third example. It is often stated that 10% of the population is left-handed. A researcher is suspicious of this claim and thinks the percentage may be different than 10%. He takes a random sample of 750 people, of whom 98 are left-handed. We will let alpha equal 0.05. Okay, let us begin by defining our population parameter and stating our hypothesis. In this case, our population parameter will be p, the proportion of all people who are left-handed. Our null hypothesis will be p equal to 0.10, and our alternative hypothesis will be p not equal to 0.10. Remember, in the original problem, we saw the word difference. that is a good indicator that our alternative hypothesis will be not equal to. Next, we can go ahead and calculate our test statistic and p-value. But before we do that, we should go ahead and check our assumptions. Now, we are taking a random sample of 750 people, of whom 98 are left-handed. Without even having to do the math, I know that n times p naught, which is 750 times 0.10, is going to be greater than or equal to 50. Excuse me. It's going to be greater than or equal to 5. And conversely, n times 1 minus p naught, which will be 750 multiplied by 0.90, will definitely be greater than or equal to 5. So this checks out our assumptions. We clearly have a random sample, so we can go on and calculate our test statistic and p-value. So our p-hat in this situation is going to be 98 over 750, which will equal 0.13. Now that we have all the required information, we can plug in and calculate our z-score, which will be equivalent to 2.74. Our p-value in this case is going to be the area under the curve for our two tails at less than negative 2.74 and greater than positive 2.74. We will add up our two areas to get our total p-value. In this case, we can easily use StatCrunch by going to the normal calculator, plugging in a mean of 0, a standard deviation of 1. If we want to go ahead and put greater than or equal to 2.74, which is just the right tail, we will get a value of 0.00307,196. We can go ahead and round that to 0.0031. Now, if you recall, the area to the right and the area to the left are going to be equivalent, so we can go ahead and just multiply by 2. This will give us a p-value of 0.0062. This means that it's decision time. Since our p-value is 0.0062, and that is clearly less than our alpha value of 0.05, we can go ahead and reject our null hypothesis. At the 5% level of significance, we can conclude that we do have sufficient evidence to say that the percentage of people in the population who are left-handed is different from the stated 10%. Okay, so this brings us to the end of Objective 1, and we can begin our understanding of Objective 2, conducting a hypothesis test for difference in two population proportions, P1 minus P2. An example of this situation would be, does the proportion of smokers with lung cancer exceed the proportion of non-smokers with lung cancer? A second example was, does the proportion of urban voters who support candidate A differ from the proportion of suburban voters who support candidate A? Our stated hypothesis for this case would be a null hypothesis of P1 minus P2 equal to 0. And our alternative hypothesis can be P1 minus P2 not equal to 0, P1 minus P2 greater than 0, or P1 minus P2 less than 0. You may be wondering, why are we comparing our values to 0? Let's think about this logically. If we have P1 minus P2 equal to 0, using algebra, we can rearrange this such that it is P1 equal to P2. The same thing for our alternative hypothesis. What we're really saying is P1 is not equal to P2, P1 is greater than P2, or P1 is less than P2. This is just an alternative and considered to be a more proper way of writing on a hypothesis, although the statements are the same. If we recall from Chapter 9 and Lecture 20, for large samples, our z statistic is going to be the quantity of p1 hat minus p2 hat n quantity minus p1 minus p2 n quantity over the square root of p1 q1 over n1 plus p2 q2 over n2, which will approximately follow the standard normal distribution. If the null hypothesis is true, which is what we are assuming when we conduct our hypothesis test, then P1 equals P2 equals P. And therefore, our hypothesis test statistic will be Z equal to P1 hat minus P2 hat all over the square root of PQ times the quantity of 1 over N1 plus 1 over N2, which again, we will assume follows the approximate standard normal distribution. Unfortunately, we don't know what P is, so instead we're going to use a pooled estimate of P, which will be P hat equal to x1 plus x2 over n1 plus n2. So the statistic for our two-sample z-test for proportions that we'll use is going to be z equal to p1 hat minus p2 hat all over the square root of p hat times q hat times the quantity of 1 over n1 plus 1 over n2. We can notice that our test statistic is a z-score, so we can use the standard normal distribution to find our p-value. We'll need to check our assumptions. First, we make sure that we have an independent random sample, and this must come from two large populations such that n1 p1 hat is greater than or equal to 5, n1 times 1 minus p1 hat must be greater than or equal to 5, n2 p2 hat is greater than or equal to 5, and n2 times 1 minus p2 hat must be greater than or equal to 5. To understand all that we've just learned, let's take a look at an example. We can say that the Proposition B is on the ballot in the county. 120 out of 200 voters within city limits are in favor of Proposition B, while 260 out of 500 voters outside of the city limits favor Proposition B. Do we have evidence that the proportion of city voters who favor Proposition B is higher than the proportion of voters who live outside of the city limits? Let alpha equal 0.05. Let's begin by identifying our two groups. So let group 1 be the group that lives within our city limits, and group 2 be those who live outside of the city limits. Our parameter of interest will be P1 minus P2, the difference in proportion of all voters within city limits and the proportion of all voters outside of the city limits who support our Proposition B. Our hypothesis in this case would be a null hypothesis of P1 minus P2 equal to 0 versus the alternative of P1 minus P2 greater than 0. If we scroll back into our original problem, remember we are asked, do we have evidence that the proportion of city voters who favor Proposition B is higher than the proportion of voters who live outside of the city limits? Now, we need to check our assumptions. Are we dealing with a large sample? Checking our assumptions, we can see that all are greater than 5. So we can go ahead and use our normal distribution. Let's begin by calculating our p hat value so we can go ahead and calculate our test statistic. Recall our p hat is equal to x1 plus x2 over n1 plus n2. This will give us a p hat value of 0.54 and therefore a q hat value of 0.46. Now plugging in our known information, we will have z equal to 0.6 minus 0.52 all divided by the square root of 0.54 times 0.46 multiplied by the quantity of 1 over 200 plus 1 over 500. This will give us a z-statistic of 1.92. If we recall, our alternative hypothesis was P1 minus P2 greater than 0. So our p-value is going to be the probability of z greater than 1.92. Since we're going to have to use our z-table, unless we choose to use our z-statistics on StatCrunch, we will need to find the alternative, or the complement rule, and find 1 minus the probability of z less than or equal to 1.92. This will give us 1 minus 0.9726, or a p-value of 0.0274. Now we can go ahead and make our decisions. Since our p-value is 0.0274, which is less than alpha, we can reject our null hypothesis. This will lead us to have the conclusion, at the 5% significance level, we do have sufficient evidence to say that the proportion of city voters who favor Proposition B is higher than the proportion for voters who live outside the city limits. All right, this brings us to the end of the lecture. Let's just do a quick summary. The binomial distribution can be used to test a claim about a population proportion when you have a small sample. A 1 proportion z-test can be used to test a claim about a population proportion when you have a large sample. A 2-sample z-test for proportions can be used to test a claim about the difference between 2 population proportions when you have large samples. All right, as always, if you have questions, send me an email. Good night.